Equilibrium. What does the word equilibrium mean to you? As a child, if you ever played on a seesaw with your friend, and you may have noticed that when you are both in mid-air, there is a likelihood in perfect condition where both you and your friend on the opposite side could be suspended in mid-air for a few seconds before that balance is lost and one side eventually comes down. We can say that while you are both in mid-air, that is a situation where both of you are in equilibrium. That would be an equilibrium having to do with mechanics, but chemistry also has its own equilibrium. We call it chemical equilibrium. And let's study what exactly that is. Now, equilibrium in chemistry, first of all, could be a physical equilibrium or a chemical equilibrium where chemical reactions are involved. Physical equilibrium has to do with two different states of matter coming into contact with each other. For example, if you dissolve oxygen gas in liquid water in a lake, for example, there might be equilibrium associated there. We'll talk about what that could be in a few seconds. Stalactite and stalagmite formation in a cave, and even when sugar dissolves in water, there is equilibrium involved there. Equilibrium processes are reversible processes or reversible reactions that occur in both directions. In fact, you have already seen equilibrium processes when you saw this reversible arrow used for weak electrolytes when we were studying them. Weak electrolytes such as acetic acid breaking up into H plus ion and acetate ion. And equilibrium processes are dynamic processes. Reason is it's not coming to an end. There is no standstill like it would be if you were on a seesaw, and instead there is constant motion, except even though there is constant motion on both sides, there is no net change. Now I said a lot of things which may not make sense, but they will make sense in a second as we look at the next slide and study this situation. Let's say you dissolve sugar in water. First, you add 2 to 3 grams of sugar in 100 milliliters of water. Well, what do you notice immediately? With your eyes, you can see that as you are stirring for a short time, all the solid sugar begins to dissolve, and in a few seconds, all of it is gone. You can express that process, that physical process, by this reaction. Sugar solid turning into sugar aqueous, meaning it dissolved. This is not an equilibrium process because notice the arrow is only pointing to the right, and as I said a few seconds ago that you need the arrow to be a reversible arrow for it to be a equilibrium process. But then after you added 2 to 3 grams of sugar, let's say you continue to add sugar until you add or you try to add 100 grams of sugar in 100 ml of water. And you may not know this, but that much sugar cannot dissolve in 100 grams of water. Much of it will dissolve, but a lot of it will be left over. In fact, you will be able to see that with your eyes. You will be see it piling down on the bottom of the sugary liquid water where you have remaining sugar that's undissolved. Now, to your naked eyes, it appears as if nothing is happening. All that sugar that you try to dissolve, no matter how much you stir it, just remains there and nothing is happening. And if you stop stirring it, you can look at it and it will be as if there is no movement. However, equilibrium is dynamic. Dynamic equilibrium means there are changes that are happening, but there is no net change that's happening. What does that mean? What it means is the sugar that's piling up at the bottom of the glass in which you have sugar water, well, that sugar is converting into dissolved sugar with time. However, inside the solution, inside the liquid portion where you have sugar dissolved, that sugar is also coming back and precipitating into the solid sugar. And the amount of both directional changes are equal to each other. Meaning, for example, if in 1 second I have 1000 molecules of solid sugar dissolving, then within that same second, some other already dissolved 10,000, I mean 1000 molecules of already dissolved sugar are precipitating back into the solid. So change is happening, but there is no net change. You can say it that way, because certain molecules are dissolving while other molecules are precipitating. However, there is no net change over time, so that pile remains the same. This is why we call it dynamic equilibrium. It's dynamic because there is still movement happening. It is not static. Nothing has completely ceased from happening. That's why it's dynamic. And it's equilibrium because we are at a situation where things are in balance now, so to speak. We have certain amount of solid sugar that is not changing as a total amount, and certain amount of dissolved sugar that is also not changing. And whenever we write this reversible arrow, we are saying that this is a reversible process, a dynamic equilibrium process. When we are using the weak electrolyte equations to show the same thing, what we were saying was that we are getting products on the right side, and those products are converting back to reactants at some point. And at some point, the rate of the forward step is going to equal to the rate of the backward step, the reverse step. And we'll talk more about it in a few seconds. So continuous change is taking place without any observable change in the amount of sugar in either the solid or the dissolved form. So in a chemical equilibrium, we have chemical reactions. The equilibrium we just talked about with solid sugar in equilibrium is aqueous sugar. That's a physical process because it's not a chemical reaction involved. Nevertheless, physical processes also have equilibrium associated with them, similar to examples given here: dissolved oxygen in the lake, stalactite and stalagmite formation as well. Dissolved oxygen may be in equilibrium with undissolved oxygen in the air, and stalactite and stalagmite formation is in equilibrium with the starting particles that form them in the first place. So, what exactly involves a chemical equilibrium? A chemical equilibrium is a state where the rate of the forward reaction is equal to the rate of the reverse reactions. We looked at rates when we were studying kinetics. How fast things happen is very important in chemistry. Well, chemical equilibrium is established when the forward reaction, meaning the reactant is turning into products, if the speed at which that is happening, if the rate at which that is happening is going to equal the same rate as the products turning back into reactants. If the two rates are equal, then there will be no net change. The amount of reactant that turns into the product in a given amount of time, within that same time period, the same amount of product will turn back into reactant. And so overall there was no net change. Yet there was no complete ceasing of all chemical processes. There were chemical processes happening, except they did not produce any net change. We say that such reactions do not go to completion. When we write those non-reversible arrows pointing only in the right direction, from the left to the right, we are saying that all of our reactants go and turn into products, with no products turning back into reactants. There is no way for the products to turn back to reactants by establishing some rate, converting them back to reactants. The reverse rate is never able to match the forward rate. So here is a reaction of ammonia and hydrogen gas to produce, a nitrogen gas and hydrogen gas reacting to produce ammonia. this reaction is actually conducted in a process known as Haber process, which is one of the precursors to our modern fertilizer productions, because ammonia is very necessary to produce fertilizers. Now this reaction takes place at a very high temperature, and in this reaction you have nitrogen gas breaking the bonds between the two nitrogens, and three molecules of hydrogen gas breaking the bonds between their individual molecules, and rearrangement takes place where all of them link together in this way, in a way that you produce ammonia, where a nitrogen is linked with hydrogen three times over. So this reaction is actually an equilibrium process. If we carry out this reaction at high temperature and we have a certain amount of nitrogen and hydrogen gas in the beginning and nothing on this side, we don't have any product yet, over time we are going to make ammonia. But as we start making ammonia, we will start accumulating the amount of ammonia we have here. And at some point, ammonia is going to start to break apart and form hydrogen and nitrogen gas. Now, initially, when we have just started this process, we have very little ammonia. So, because we have very little ammonia, very little of it can turn back and form hydrogen gas and nitrogen gas, while at the same time we have lot of nitrogen gas and hydrogen gas. But as the reaction proceeds, what is happening in the forward direction? What's happening is we are using up nitrogen and hydrogen gas and making ammonia. So the amount of nitrogen and hydrogen goes down while the amount of ammonia goes up. Well, as the amount of ammonia goes up, so does the rate at which it gets to convert back into nitrogen and hydrogen. We can show this in a graph form shown here, which depicts the progress of the reaction and the rate of the forward reaction and the rate of the reverse reaction. So initially, at the beginning, notice we only have very high concentration of hydrogen gas and nitrogen gas, while zero concentration of ammonia. As we learned when we studied kinetics, that rate can be expressed by using the rate law, in which we have rate constant K times the concentration of the reactants and raised to some exponents on each, which can be found out through experimentation. Well, according to that rate law, the rate depends on the concentration of the reactants. So initially we have very high concentration of nitrogen and hydrogen. So the rate of the forward reaction is very high, while we have no ammonia to begin with, so the backward rate would obviously be zero. But as time goes on, we consume nitrogen and hydrogen to produce ammonia. So the amount and the rate of the backward reaction, the rate of the forward reaction goes down. Now, why does the rate of the forward reaction go down? Because the concentration of nitrogen and hydrogen go down. Hence, the rate goes down. At the same time, the rate of the backward reaction starts to increase, the rate of the backward or the reverse reaction, because as we consume hydrogen and nitrogen, we produce ammonia, and as more gets produced, the rate, which depends on the concentration of this product, will increase. Eventually, they will both coincide at some point where the rate of the reverse reaction, the reaction consuming ammonia, is going to equal to the rate of the forward reaction, the reaction consuming hydrogen and nitrogen. Because they are both being consumed and produced at the same rate, there will be no net change. And that's the point of equilibrium. That's the point where we have come to an end in terms of any net change. At equilibrium, reactant depletion and product depletion happens at the same rate, so there is no net change. In the next video, we will actually come up with an expression for equilibrium, and that will make things much easier for us to actually see chemical equilibrium as a mathematical process.